In this pair of videos, we're going to go over 4 different strategies that you can use to help you balance the more complicated types of chemical reactions that you may see. The first of which is what we call the major hydroxide or major OH strategy that simply involves balancing the major atoms within a chemical reaction followed by the atoms in hydroxide, that being hydrogen and oxygen. So when we say major atoms, a major atom is simply any atom within the reaction that is not hydrogen and not oxygen. So in the case of our first reaction here, there is only one major atom, which is phosphorus, which we see is very easy to balance because we have 4 phosphorus atoms in the reactants and only 1 in the products, so we can fix this by putting a balancing coefficient of 4 here, and now our phosphorus is successfully balanced. Now, the reason why I wrote hydrogen first and not oxygen is if we look at our reaction, we see that the difficulty of balancing oxygen is that oxygen can be found in more than one location, so it's difficult to know where to add a balancing coefficient, whereas with hydrogen, we see that we only find it on one atom in the reactants and one atom in the products. So that's why we're starting with hydrogen first, but the opposite might also be true of balancing oxygen first if we can find hydrogen in more than one location. So in our products, we see that we have 4 times 3 is a total of 12 hydrogen, and then we have only 2 here, and we know that 6 times 2 is 12 hydrogen, so now our hydrogens have been balanced. And once we've done this, we can take a look at something interesting that's happened with oxygen. So in our products, we have 4 times 4 is 16 oxygen, and then if we look in the reactants, we have 10 oxygen in our second compound and 6 oxygen in water, and 6 plus 10 is of course 16. So oxygen is balanced even if we didn't have to do anything additionally. So if we add a balancing coefficient of 1 here, we can see that following the major hydroxide or major OH rule seems to work relatively well. Now if we take a look at the chemical reaction below, we see this reaction looks significantly more complicated, but is actually significantly easier to balance if we approach it with a particular strategy. Now we see that all of these compounds look like they have relatively complicated formulas until you see what I've underlined, which are all of the polyatomic ions. So in some situations, it is possible to keep all of the polyatomic ions together, and rather than focusing on balancing the individual atoms, for example, balancing phosphorus, balancing oxygen, and balancing hydrogen, if we treat all of the polyatomic ions as individual units, the reaction actually becomes easier to balance. This is especially true whenever we're dealing with any displacement reaction, whether it be a single or a double displacement reaction. And again, in this case, we see that it is definitely a double displacement reaction because we have our AB compound here and our CD compound here in the reactants. So if we follow the major hydroxide strategy, keeping in mind that we can keep the polyatomic ions together, we wouldn't start by balancing phosphorus, we would start by balancing phosphate. So we see in the products that we have 4 phosphate here in this titanium phosphate compound, but we only have 1 in this acid that we see here, so we can add a balancing coefficient of 4, and now our phosphates are balanced. We can also balance titanium because it's a major atom. We have 3 titanium atoms in the products, but only 1 in the reactants, so let's give this a balancing coefficient of 3. Now, we see that water is actually one of our products, and we also see that we have a compound that has OH minus, hydroxide in its structure, and we see another compound that begins with hydrogen H+, which means that we have a base and we have an acid, meaning that we are dealing with a neutralization reaction here because we recognize that we have a salt compound and water. Now, this is where keeping the polyatomic ions in mind will actually help us balance, because even though water is written as H2O, it helps to think of water as H and OH separately, again, keeping the polyatomic ions together. So in the reactants, we see that we have 3 times 4 is 12 hydroxide, and then in terms of hydrogen, we have 4 times 3, which is 12H+, meaning that if we have 12 OH- that combine with 12H+, we get 12 water. So as we've seen here, as long as we follow the major hydroxide strategy and group our polyatomic ions together, we can see that balancing this neutralization reaction is relatively easy to do. So if we add a coefficient of 1 to our salt, we see that we have successfully balanced this reaction. In the next video, we're going to be focusing specifically on strategies that are used to balance combustion reactions, as for many students, combustion reactions are the largest headache when it comes to balancing.